So, could you explain us a little bit about this experiment?
Right, so the purpose of this experiment is to locate the dominant acoustic reflectors within a room, such as this wall, using an uncontrolled source, such as a click, a clap, the sound of a cup being put down, something that's impulsive in nature and very easy to produce.
Okay, and what kind of equipment are you using for this?
We have here a 4-element linear microphone array consisting of 4 microphones placed at 16 centimeter intervals and a 5th microphone placed outside the line on a plane. And the reason for this is to resolve the front-back ambiguity that is inherent with linear array processing. The microphone signals are amplified with an RME Octamic, digitized with an RME Fireface, and then analyzed with a PC running MATLAB.
Right, and what kind of processing goes in the computer?
So when an acoustic impulse is produced, the signal that's received at the microphones can be decomposed into 2 regions. The first region is due to the direct path propagation of the sound from the source to the microphones in turn. The second region is due to the reflections, whereby the sound propagates from the source to the reflector to the microphones. And what we aim to do is use the time of arrival of the reflected paths so as to form a series of elliptical constraints. These ellipses are parameterized by the location of the source, the location of the microphones, and the time of arrival of the reflections. And what we can do is prove analytically that the common tangent of these elliptical constraints corresponds to the location of the reflector. Now, there are 2 big problems associated with using these uncontrolled sources. Firstly, we don't know when they occurred. All we know is the time difference of arrival received at each microphone. We also don't know where the source is relative to the array. So the first step is to locate the source relative to the array using the time difference of arrival information. Once we've done this, we can then estimate the time of arrival of the reflections, formulate these elliptical constraints, solve for the common tangent, and then locate the reflector.
Great, could you perhaps give us a demonstration on this?
Okay, so what we see here is a model of the room where the 5 stars locate the microphones within the room. Now, I'm going to make a clicking sound. So what we see is that within the first step, the source is located relative to the array. In the second step, we then formulate the elliptical constraints, and then as a final step, find the common tangent of the ellipses. And in this example, we can see that the wall behind me has been located and the wall in the corner to the left of me has also been located.
Okay, and what is this actually good for? I mean, what is the application scenario of this?
So we can imagine that we have a home cinema set up. Now, one of the problems with home cinema is that the rooms are not very well designed. There are lots of reflections from walls and windows, tables, all sorts of things, and these contribute to the reverberation, and this reverberation spoils the listening experience. So what we can imagine is that we have a device like this that over time learns where the dominant reflectors are, and we want to use this information to our advantage. If we know where they are, then we can have a go at pre-equalizing or compensating for the reflective paths, suppressing them, and thereby improving the listener experience.
Great, thank you very much.
Thank you.